on its surface, underground there could be life. Unfortunately, the current generation of instruments and rovers is incapable of digging more than scratching the surface, more than a few centimeters down. So we're going to have to use some ingenuity to get to these places. And in fact, there are enough missions planned for Mars that it's actually going to get pretty crowded. Planets are interesting potentially for life, but what we've learned in the last few decades is that the moons of the giant planets, not the giant planets themselves, because they're mostly hydrogen and helium. They're made of what the sun is made of. They may have rocky cores, but those rocky cores are probably very inhospitable. But some of the moons of the giant planets are equal in size to the small planets of the inner solar system. They have separate sources of heating from tidal flexing caused by their parent planet, and so satellites or moons have become just as exciting to look for life in the solar system as terrestrial planets. I'm out of control. Satellite strong from the moon. Satellite that will orbit your mind till you're I pass satellite. What you're looking at is the fractured ice flow surface of Europa, one of the Galilean moons of Jupiter. The smallest feature is seen here about 100 meters across. So this is a tortuous landscape which sequential imaging indicates is moving. It's flexing like an ice flow would that has liquid beneath it. And the best models for Europa suggest that it has a 500 meter to kilometer thick ice crust on top of a tens of kilometer deep ocean. So this is a water world, a fully covered water world under ice. And although it's extremely cold, there is a tepid heating source from the moon itself, from geological heating. And so this is a cryogenic biosphere issue. There are many places we're finding in the universe where it's pretty cold, but it's not so cold that we couldn't imagine low levels of biological activity. In fact, there are missions planned to go under by landing on the ice pack, using heating from a nuclear power plant to melt through and release a hydrobot to look for life. This mission is currently unfunded, but NASA's had the design for a decade. Another fascinating place to go, we got a taste of in 2005, is Titan. And you look at the surface of Titan, and it is terrestrial in appearance. There are not just dry or arid river deltas as on Mars. There are river deltas with liquid in them. There are shallow seas. There are clouds. There's cryovolcanism. It's an active moon. It's a moon with an atmosphere thicker than the air you're breathing, made of mostly the same stuff, nitrogen. Here's what the lakes of Titan look like from the radar imaging.
Titan is the only planetary body besides Earth that we know has lakes. At 290 degrees Fahrenheit below zero, the only liquid that makes sense there is a combination of methane and ethane. This lake is Ontario Locus in Titan's southern hemisphere. It's a little smaller than Lake Michigan. We've colored the lake black because we think that's probably its real color, although we don't really know for sure. We've exaggerated the heights of the shoreline features to make them easier to see. Notice these hills, probably made of water ice. See how the liquid has flooded up the valleys? Further north is a long, smoother beach that looks like it's been shaped by waves. You can see some lines along the beach that might be old shorelines, like bathtub rings, so we know the level of the lake has changed. Now we're turning east to a very obvious bay that cuts into the beach, so it's likely to be younger. We'll cross over the lake. You'll see some flooded valleys, and in the background is a large river that makes a delta, like the Mississippi River. Its shape means the lake is shallow and the river is slow. Ontario's shore is surprisingly like earthly lake shores. Pretty amazing to find something this Earth-like 800 million miles away.
Another place we'd love to go back to, NASA has a mission planned for this too, also unfunded and at least a decade away. Planetary scientists, my colleagues over at LPL, are somewhat frustrated by the long timelines of doing these missions. But you are going a good fraction of a billion miles, high degree of difficulty, expensive, always a risk of failure. But some people think, although we don't know, that ethane, methane, plus some water and ammonia, especially below the surface, is a plausible basis for a very strange and unusual kind of biochemistry. If there was life 2.0, this might be the place we find it in the solar system. And then we've been surprised by the fact that there's water in places we never anticipated. Tiny little Enceladus, 500 kilometers across, no bigger than Rhode Island, a far too small moon to be interesting to most planetary scientists, turns out to have geysers that are sprouting to the surface and then ejecting ice particles into space, where they've been sampled from Cassini and shown to contain salt and other interesting chemicals. And if you do a full census of all the small bodies in the outer solar system that might have the three ingredients for life, the bare minimum, organic material, liquid water, and available energy, the number's about a dozen. Most of them are unexceptional moons of the giant planets. And the liquid water, of course, is under the surface in these cases. But that's a pretty interesting inventory. So it's certainly not just Mars that's a potential place for microbial life in the solar system. But in the last 15 years, we've started to discover planets elsewhere. So rather than just looking in our backyard, we have a whole vast amount of new real estate to inspect for life. Now, this is very early days. We only started to find planets beyond the solar system, as I said, 15 years ago, and they came in at a dribble. Now they're becoming a flood, and they're starting to get what I would call interesting in their nature.
The return of Saturn. Jupiter. I'm your Venus. I'm your fire. Hey, Jupiter. Nothing's been the same. There's a new planet in the solar system.
These planets, when we started to find them, surprised us because they were usually large, massive, more massive than Jupiter, on incredibly tight, hot orbits of their parent stars. So we started to look around sun-like stars, hoping to find proxies for the solar system, and what we found was really quite different. Here's an example. This is a system, actually the first solar system found, a system of 4 gas giant planets, and a little visualization of where it exists in the constellation of Cancer, looking out in that direction to the 55th brightest star in the constellation. If you visualize leaving our solar system and then doing a little warp speed thing about 40 light years, you end up in another star system, and there 4 planets sit going there around their sun-like star. They're all between the masses of Neptune and Saturn. The record holder now is a system with 7 planets. And that given that Pluto has been demoted, that's almost as many planets as our solar system. So this is becoming very mature science. We're finding systems of planets, mostly still large planets. This is the story so far. 530, I looked it up last night, 531 exoplanets. In 1995, none. All in the last 15 years. And you can see several things. First, you can see that most of these planets are still massive. They're still Jupiter-like or even more massive. But the detection limit, the threshold, the smallest thing we can detect, has marched steadily downward and is reaching Earth mass, just last year, essentially. The game is just getting really interesting. The record holder, Gliese 581e, is just under twice the mass of the Earth. So we're starting to go from gas giants, which we would never expect to be habitable, although their moons might be, we just don't have a way of finding their moons, down towards terrestrial planets, things that are Earth-like. And I'll come back to that space in a minute. The method has been indirect detection. A planet around a nearby star reflects about 100 millionth of the light. If it's an Earth, a billionth of the light. And it sits so close to the star, it's like trying to see a firefly next to the floodlights of Arizona Stadium. So the method that was used was an indirect method where we look for the wobble induced on a star by the orbiting massive planet. In the case where that happens in the equatorial plane, we get an extra way of detecting it. We get the Doppler shift from the wobble of the star, and we also get a periodic eclipse where the light from the star dims according to the size of the planet. And that works like this. For a Jupiter crossing a sun-like star, the brightness will dip for about 5 hours, in fact, once every 12 years by about 1%. That's easy to detect. Earth will make a signal 100 times smaller, so 1/100%. And it sounds hard, but that can be done. And that's what the Kepler satellite was designed for. And I'll show you the results from that. So this has become a very powerful technique for not only measuring planets and finding their mass, but also the size of the planet, because the depth of the eclipse tells you the size of the planet. And size plus a mass gives you a density, so you learn something extra. And what we've learned is that nature makes an extraordinary variety of planets. Almost everything that theorists could hypothesize has been found at this point. We've not really found pure water planets, but we found planets that are probably 50 or 60% water ice and the rest rocks. We found planets that are 80 or 85% metal mixed in with a little rock. So extraordinary composition variations of planets. And indeed, many are just like the sun and are mostly hydrogen and helium. So it's a kind of a wild world out there, and the level of information is not always what we might want to discriminate between these possibilities. The goal, of course, is to detect Earths. That's when it gets interesting. So let me give you the state of that game. Here's what simulations tell us. This is a simulation where things that are 100th the Earth mass, planetesimals, are gradually glomming together by gravity, just by simple accretion of running into each other and sticking by gravity, into a smaller number of large things. And so this is a simulation, a full gravity simulation, and you can see how quickly, starting from small chunks, you build up to Earth-like planets. This is a simulation, of course, and it's not expected that you generate the inner solar system. But you can run this simulation hundreds or thousands of times and see the diversity of terrestrial planets. And what you find when you run all these simulations is pretty much what you see here, that in general you get between 2 and 5 rocky terrestrial planets, and typically 10 to 20% of them are in the habitable zones of their stars. So simulation, pure theory, is telling you you should expect essentially all sun-like stars to have a couple of rocky planets and 10% roughly of them to be in the habitable zone and therefore potentially have liquid water. It's a very exciting number, but that's theory. What does the data say? Here's the data from just a month ago from the Kepler satellite finally releasing Earth-like planets for the first time. So you saw the 15-year history of this subject until a month ago. Here's the data that NASA released in a press conference quite recently. Kepler is looking for these small eclipses, and because it can detect a very subtle eclipse, it can find Earths, and the proof is right here. But Kepler has only been working for a few months, and so these Earth-like planets are, of course, in orbital periods of a month, maybe 2 months. So they're going around their stars faster than Mercury, and so they're hotter than Mercury. So we have to be patient. We have to wait until Kepler's worked for a couple of years before it can find an Earth in an Earth-like orbit. But this tells you that they're there. They're there to be found. We just have to be patient for the satellite to bring them in. And the other exciting thing from these results is that the number of planets increases rapidly towards the detection limit. So for every Jupiter or Saturn-like planet, you actually expect many Earth-like planets. Rocky terrestrial planets are abundant. They're not rare at all. Going back to simulations, the simulations allow us to follow the water in a simulation, so we can see where these rocky planets, what water content they have. And you might think the Earth is a water planet. We think the Earth is special. We talk about it as the water world and think that it's special for that reason. And certainly Mars is dry and Venus is baked dry. But these simulations tell us that in general, terrestrial planets will have as much as the inventory of the Earth's oceans, maybe even 10 times as much, maybe 100 times as much. Remember, water is not a rare ingredient. So we have everything we need. We have abundant rocky planets beginning to be found by Kepler. We have some fraction of them, a significant fraction, in a habitable zone where liquid water can be on the surface, And models tell us that that liquid water will be there. It'll be part of the composition of the planet. It's very